Hello and welcome to lesson 3.4. So there's going to be a couple, two or three parts to this lesson. So the quote today says, as long as algebra is taught in school, there will be prayer in school. Although there isn't really prayer anymore in school and algebra is being taught less and less. So I think this quote's becoming a less and less relevant. So it says it's no secret that alcohol consumption by college students is common and that overindulgence can have many negative effects in both the short and long term. And if anything, the problem is getting more serious. At my school alone, 21 students were hospitalized for alcohol poisoning during one recent weekend. When someone makes a choice to drink, they're affected as long as the alcohol remains in their bloodstream. There are many theories on how to hasten the sobering up process. Black coffee, ice cold showers, greasy food, drinking lots of water. The truth is that none of these has any effect whatsoever on blood alcohol concentration. That's called BAC. You can try every mythical treatment known to man, but at the end of the day, the only thing that will bring down BAC is time. So far, we've studied a wide variety of quantities that can be modeled using linear equations. In this lesson, we'll use time required to sober up and other quantities to study writing linear equations that model expressions in greater depth. But first, let's talk about something much more positive, pizza. Hmm. So when a person drinks, how do you think alcohol leaves the body over time? At a steady rate or some other way? So as time goes on, your BAC, I would assume if it starts out high, I would think that it goes negative in some fashion. I don't know if it goes really quick or gradually, but I definitely think it's a gradual left to right, it's going down. So let's jump into pizza. It says a student org you're involved in is planning a year-ending pizza party to celebrate another successful year on campus. As chair of the planning committee, you've wisely worked a deal with a local pizza place to provide large pizzas at $9 each. The budget will allow at most $175 to cover the food. And of course, you'd like to know how many pizzas you can get and stay under budget. We'll attack the problem in several different ways. Using a numerical calculation and include all details and don't forget to write the number of pieces you can buy. So you might start by saying, if I know each pizza costs $9, I might start by doing some guesstimating. So two pizzas would be $18. 10 pizzas would be $90. Um, And if we double that, that's 180, so that's too much. So you might be doing some guess and check. That might be one way. The other way would be to, instead of using multiplication, to use division and say, if I can spend $175 divided by the $9 per pizza, then we would find out that we could buy 19.44 pizzas. But you can't really have 0.44, right? So we could have 19 pizzas with a little money left over. Okay. Write an equation that represents the total cost of ordering P pizzas. Remember, each pizza costs $9. So we're not worried about how much we have to spend. We're just looking at the cost. So the cost equals $9, but we don't really need the symbol there, but $9 times the number of pizzas. So we can let that represent that. So number 3 says, complete the table here. So if we bought 0 pizzas, we would have 0 times 9. So our cost would be 0. And if we bought 5 pizzas, we would have 5 times 9 or $45. 10 times 9 would be $90. 15 times 9 would be $135. 20 times 9 would be 180. 25 times 9 would be 225, and 30 times 9 would be 270. Okay, so we could put these into Desmos if we wanted. And I'm going to share my screen. Okay. And over here, what I'm going to do is I'm going to make a table. And in my X1, I'm going to put the number of pizzas. So we were going by fives, and the computer knows that. So right there. And then we said our rule, right? We can put, if we know the rule, we could type the rule up here. And we said the rule was 9 times the number of pizzas. So we're going to say 9 times our column that we use. So 9 times X1. So there's our data right there. Then we can go ahead and press the Zoom Fit button, and it plots our graph for us. And of course, I'm going to save this as QR lesson 2 for pizza. And I'm going to make a little folder here that says pizza part 1. And I'm going to drag that in there. Okay. Now I'm going to go back to my graph on my paper here. So we graphed it on the screen. It says, since we want to spend at most $175, this is a good place to use an inequality. An inequality meaning something like this. Write an inequality that can be used to find the number of pizzas you can buy for at most $175. Then solve that inequality and use the result to decide on the number of pizzas you can buy. So that means we want our cost to be less than $175. And we said that cost equals $9 times P. So that means we need the $9 times P to be less than, actually, or equal to 175. And there is a multiplication going on right there. And to undo multiplication, we're going to use division. So if I divide both sides by 9, I can solve for P. And we already did this on page 1 as an intuitive thing. And I'm dividing by positive, so I don't have to flip my symbol. And so this is where we get 19.44 or 19 pizzas. It says, what is the slope of the line you drew in question 4? What does it represent? So the slope is the $9 per pizza. And when I say M, that's because in linear equations, we usually write a linear equation like this. Y equals mx plus b, where m is the number being multiplied by the variable. And so we had c equals 9p plus 0. We really had plus nothing. So 9 is our slope. And slope is always really a change in your y over your change in your x. So for us, this means that for every pizza, right, because pizzas is my x, money is my y, and pizzas is my x. So for every one increase on pizzas purchased, my money cost is going up by $9. So for every one pizza purchased, my cost is going up by $9. What's the y-intercept of the line? So the y-intercept is where we're crossing the y-axis. So we said that was right here. And these are pizzas. 5 is at, we'll do 10, 20, 30, 40, 50, 60. Oh, I'm not going high enough, but it was on our graph. So we were at five pizzas and $45 right here. But right here is our intercept. Our y-intercept was at 0, 0. And you can see that here, the y-intercept is b. It's when x is 0 and the b value in your linear equation. So for us, it's 0, 0, which means when I have not purchased any pizzas, my cost is $0. That's pretty cool. Okay, now we're changing it up a little. It says, nice job so far, but did we forget to mention there's a $10 delivery charge? Sorry. You'll have to rework the problem, keeping in mind that we want to know how many pieces we can get at most for $175 at $9 each, plus this flat fee of $10 for delivery. Write an equation that describes the cost of buying pizzas with the delivery charge. So if we go back to our original equation, we said the cost was $9 per pizza. And now we just have to add on this fixed cost that is not influenced by the number of pizzas. It's just a flat $10 fee. So we're going to add $10 at the end. So that means even if we don't buy any pizzas, we still have to pay this $10 cost, right? That's kind of how we're thinking about it. But then once we buy 5 pizzas, we're going to have 45 for the pizzas plus $10. So it's going to be 55. And then if we buy 10 pizzas, it's going to be $90 plus 10 or 100. If we buy 15 pizzas, we said that that was going to be 135 plus 10 or 145. If we bought 20 pizzas, that was going to be 180 plus 10 or 190. And 25 pizzas was going to be 225 plus 10 or 235. And if we bought 30 pizzas, it was going to be 270 plus 10 or 280. Okay, so let's look at this in Desmos. So over here in Desmos, my new rule is now going to be 9 times x1 plus the $10 fee. So these are the values that we just came up with. So everything has just kind of been shifted up, this $10, shifted up, shifted up. And notice that the slope, how it's growing is still the same, and that's because the price per pizza, the slope of 9 has not changed. So we made our graph in Desmos. So I encourage you to practice making that graph as well. Okay. So it says, write and solve in number 11, an inequality that can be used to find the number of pieces you can buy with the delivery charge added. Write the solution to the problem in a full sentence. So we said our cost was $9 per pizza plus 10. And we wanted to keep this under 175, under or equal to. So this is what we're comparing it to. So we're going to subtract that $10 flat fee no matter what. We're going to subtract that first, because we have to pay that no matter what. So that leaves us with the 9 times the pizza is less than or equal to $165. And now I can divide both sides by 9 to solve for P. And find out that we can purchase 18.33 or 18 pizzas. So we can buy 18 pizzas and stay under the $175 that we have to spend. It says, what is the slope of the line you drew? So we said our slope was still 9. Each pizza still only costs $9. What is the y-intercept of the line you drew? So this time the y-intercept starts. So remember, our y-intercept is always our starting value, we say. So that means when we haven't purchased any pizzas, there was still this delivery fee of $10. So we owe $10 no matter what. Now, in reality, if you didn't call and buy any pizzas, you wouldn't owe a delivery fee. But what they're saying is you're going to have to pay that no matter what. Number 14 says, now here's the key idea. Look back at your answers to 8, 12, and 13. The slope was 9, and the y-intercept was 10, and the equation was C equals 9p plus 10. And that's similar to y equals 9x plus 10. Page 175 here. It just kind of goes through a reiteration of what we just did. Talking about the coefficient is the number being multiplied to the variable, the 9. And the constant term is just like that. Constant means something that doesn't change. It's not being affected by the variable, and that is the number 10 is our constant. Okay, so this equation of the line that we've talked about is our slope-intercept form, because we can quickly grab our slope and quickly grab our y-intercept in this. So let's just do some quick understanding of slope and y-intercept. It says a small business had just 12 employees when they opened their doors, but they have been adding employees at the rate of 4 per month since then. Write a linear equation that describes the number of employees in terms of the number of months after the company was founded. So I'm going to say E is the number of employees. M is number of months. So the number of employees, it says they started with 12. That's not changing. So that's going to be my y-intercept. That's the part that's not changing. It's constant. But it says they've been adding employees every month. And that rate, so slope is the rate. They've been adding 4 per month. And month is what our x is. So 4 per x, 4 per month. 4m plus 12. What are the slope and y-intercept? So the slope m is 4. And this tells us that each month they grow by 4 employees. And then the y-intercept is always when x is 0. It's our constant, so that's 12. And so that says that they started with 12 employees. And for the graph, I would like you to practice this in Desmos. So if you can go back to your Desmos, I'm going to go to mine. And I'm going to show you that right here. So I'm going to close this out. And I'm going to do a new graph. And I'm just going to use y and x, even though we were using e and m. So y equals 4x plus 12. And this is what, in red right here is our equation for the number of employees. And if you wanted to see different X values and different Y values, then you can click on the equation here and then go up to the gear. And if you click on the gear and then click on this create table, it will make a table, which is nice because then you can kind of see how you're thinking about it. So after 1 month, that means you added 4 employees to 12, so you have 16. So that makes sense. So you can actually put in any X if you want to look after 20 months or 24 months would be 2 years, how many employees, you'd have 108 employees after 2 years. So it allows you just to put in any number of months that you would like to put in, and it can give you those values. So I encourage you to practice with Desmos because the more you practice, the more you will feel comfortable. And our project for Unit 2, remember, is going to be using Desmos. So you're going to have to turn into a Desmos file. So please reach out if you want my help. I'm happy to walk you through this again. So let's go back to our sharing here. And I just wanted to go over this solved example of graphing a line. So we learned how to graph a line just now in Desmos, but I want to go over some things so that you can kind of go back to your algebra days here. So if we had this equation here where the slope is a negative 10/3, they want us to graph this. So there's a couple things you can look at. Let's first look at if we were to put 0 in for X, then this multiplies to 0 and then we end up with 12. So we get this point here, 0, 12. We can put that on the graph. That's also our y-intercept. Remember, that's our beginning value. And you might have seen that because it's in y equals mx plus b form. So now that we have that, then we look at our slope. So our slope is a negative 10/3. It means it's going down from left to right. So every 3 we go over right, we go down 10. That's one way we can think about it. We could also just put in different values of x and figure out what y is, and then you've got some coordinate points. So they did that here. They came up with the first one we had was 0, 12. Then they put in 3 and got 2 and 6 and got a negative 8. When you're drawing a linear or a line, you only need 2 points because it won't curve at all. So 2 points and you know that you've got it drawn correctly. So I encourage you to be using Desmos quite a bit. Catch me back for part 2 of this lesson.